All right, let's do like a quick example on the series and parallel connections and see how we can actually like simplify it to find like the equivalent resistance. Example, let's just say I'm given this circuit, which is a 2K over here. It's a 4K over here. Just call this A and B. This is another 2K, followed by a 6K and a 9K here. Then we have another 6K over here, 10K, 1K, 2K, and a 6K. And the question is like, what is the equivalent resistance from this point, like from A and B? Well, if you look at it, it is very clear that like these two are in series. So I have 2 and 1 in series. So let's just call this like number 1. So number 1 means 1 is in series with like 2K. So it's going to be 3K. So the result is going to go between like this point and this point, basically. So if the result, which is this 3K, goes between like this point and this point, what it means is that if I wanted to like simplify further, I can basically take a look at these two, but these two this time are in parallel. Let's just call this like number 2. Number 2 means this number 1 in parallel with 6K, which is 3K in parallel with 6K, which means 3 times 6 divided by 3 plus 6. So it is 2K, right? If I want to simplify it further, there is going to be a resistance between this point and this point. So I'm replacing like the whole thing here. So if I want to just do like the simplification a little more, let's just call it like 3. Then number 2 is in series with this 10K. So number 3 is number 2 in series with 10K, which is 2K plus 10K, which is 12K. Now I'm going to have a resistance that's going to go between here and here. Let's just call that number 4. And if I wanted to like simplify it more, I have to have like this result in parallel with this 6K. So number 4 would be number 3 in parallel with 6K, which is 12K in parallel with 6K, which is 12 times 6 divided by 12 plus 6, which is going to be 4K. Replacing that, it means like I'm going to replace the whole thing up to this point. Let's just call this number 5. What I can see here is that I'm going to have like a resistance with the value of 4K here that has the same end as the head of like 2K, which means like they're actually in series. So number 5 would be number 4 in series with 2K. So it's going to be 4K plus 2K, which is going to be 6K. Now what I need to do is that I need to replace this whole thing. Let's just call that number 6, which is this number 5 in parallel with this 6K. So number 6 is number 5 in parallel with 6K, which is 6K in parallel with 6K, which is going to be 3K, right? Now I can replace this portion, the whole thing, with a resistance with value 3K. But if I look at it, let's just call this number 7. Number 7 is basically this 3K in series with this 9. So number 7 is number 6 in series with this 9. So it's going to be 3K plus 9K. So it's going to be 12K. And now if I replace this whole thing here, I'm going to have a 12K, which is this number 7. That would be in parallel with 4K. So number 8 would be number 7 in parallel with 4K. So it's 12K in parallel with 4K. So it's 12 times 4 divided by 12 plus 4, which is 3K. And the last step would be here. Let's just call this number 9, which is the whole thing here is replaced by number 8, which is a 3K resistance, and the result is in series with the 2K. So number 9, which is going to be number 8 in series with 2K. So it's 3K plus 2K. So that's got to be 5. Therefore, my R equivalent is 5K. Again, as you can see, like we just need to like identify the parallel and like series connections and then use the formula to find the equivalent. So the equivalent between like these two nodes A and B is 5 kilo ohms here, right? Let's do one more example. Let's just say I have a circuit that looks like this. And the question is, what is the equivalent between A and B? Let's just say this is 6K, this is 3K, this is 18K, this is 6K, and this is 10K. So looking at this circuit, the very first thing that's quite obvious is these two things in series. So that would be a 9K because they're in series, so we add up like the values. So the circuit would look like this. So I have a 6K, I have this 18K. These two, again, they go between like here and here. So I'm gonna call it like a 9K that goes exactly between those 2 points. And then I have this 10K, and this is 8. Right? Another thing that's quite obvious is like these two things that are in parallel. So if I have like these two things in parallel, it's 18 times 9 divided by 18 plus 9, which is a 6K. And then the equivalent goes between these 2 points. So if I rewrite the circuit, that would look like this. A 6K, a 10K, and that would be A and B. Now this is like quite obvious, so our AB is going to be the summation of all these. 6K plus 6K, which is 22. Again, the whole idea here comes down to the fact that we have to like determine what resistors are in series and what resistors are in parallel. If they're in series, I just add them up. If they're in parallel, we use the formula for parallel. Keep in mind, it's a remark, for resistors to be in series, they have to be back to back, back to back, and current through one is the same as current through the other one. for parallel, for two resistors to be in parallel, they should share the exact same head and tail, and voltage across one should be the same as voltage across the other. And if you go about any circuits using these two like rules, then we need to like identify like exactly like what those two like resistors are located, basically like between what nodes those two like resistors are located, and then replace that those two by the equivalent. Like in this example, we identified these two to be in series, and then we said they actually located between these two nodes. And this node is exactly the same as this. So we basically replace that with another resistance with the value 9K between those two. And we can do this for every single element in the circuit. And that's how we can like simplify down the circuit and find the equivalent.